Hello. In this video on the magnetic effects of electric current, we are going to discuss about the torque that acts on a rectangular loop which is placed in a uniform magnetic field. This concept will lay the foundation for the principle of working of a moving coil galvanometer. So let's get started with it. Now, if we consider uh, two permanent magnets, the North Pole and the South Pole, to be placed in such an arrangement, and then we have a coil which carries current. Now that coil, the magnetic field lines will obviously flow from the North Pole to the South Pole. uh, Let me indicate it with another color for better understanding, for a clear picture. So this is going to be the direction of the field, and they are constant, uh, uniform field lines that will be moving from the north towards the south. So no problems with that. This is the magnetic field B. Now if we are to place a coil such that it carries current, let us say in the clockwise sense, a rectangular coil that is. Let me draw that first. So this is more or less the case where the rectangular coil is carrying a certain amount of current, that is I, and it is placed within that uniform magnetic field. Now the coil arbitrarily is placed at certain angle with respect to the field that is moving. As you can see on your screen, the field is moving towards the right. Let's take that as the x-axis for now. And this coil that we see, that its plane is not aligned to it, and it's a bit twisted, such that if you look at the top view now, the top view, I'm going to draw the top view. So this is the top view that I'll be considering, where I've considered the magnet. That's more or less the thickness of the magnets that we have used, and this is not to scale, of course, but I'll try and draw it as proper as I can. Now this the lines of force are moving in this direction. Let me represent that by a single line, and I have the coil, which now I'm seeing that upper section or upper line of that coil. Let me name that coil first, so with naming it becomes easier. Let me name that as say MNOP. Will that be fine? I hope so. MNOP. Those are the four corners, and what I'm seeing from the top is this M and this N. I hope the picture is now pretty clear to you. The N need not be confused with the N of the North Pole, so I'm writing the North Pole in a separate color for you. So that red N is the point, or the point on that coil, while this other color, purple, so as to say, that's the color of the pole. Now in this case, with the current flowing, that small segment that we see in that line PO at the bottom, that is obviously very small, which can be neglected. That is for the inflowing and outgoing current, so that the circuit is completed. It's a circuit which is externally connected to a source, obviously, which is resulting in the current that is flowing in the circuit. And that segment, that small segment where the inlet and the outlet occurs, that gap is very, very small, and that's why it can be neglected, and we can take the PO segment to be a complete one. Now we'll be considering the forces involved when there is a magnetic field acting in a region and there is current flowing. We have understood from our previous videos that the current and the magnetic field constitute a force which acts on the current carrying conductor. So let's check those relations. Now here we will be considering 4 segments, each segment one by one, and we'll be determining the forces involved. So on that line PM, that is, we start off with PM and we end at OP, clockwise sense. So along PM, so along that PM we have the force, let us say F1 is the force which is acting on that line PM. The current is, now we have the length PM, we have the length of that section, or that, this is a rectangular loop, we have the length as L, and let's have the breadth as B, small b, that is capital B for magnetic field, small b for that breadth. Now F1 is equal to I times of L cross B, as you know. Here B is the magnetic field, of course, so L crossed with B. Now L cross B, the direction of L, as you know, is along the direction of flow of positive charge, which is the direction of flow of current. And so we'll have the direction in this case from that figure that we see over there. If you use the right hand thumb rule with the vectors, L cross B is going to be directed into the plane of the sheet that you see in front of you, the screen that you see. So this F1 is ILB sine. Now the angle obviously is 90 degrees because the L that you see from P through to M, that is perpendicular to the direction of the field, so the angle is 90 degree in that case, and that goes to 1, and it is directed into the plane. So this is cross encircled, so this is ILB cross meaning the direction of the field, the direction of the force is into the plane. So I'm denoting F1 over there as into the plane. Then we move over to MN. So along MN the current flows from N through to N. Now with this top view available to us, the magnetic field here is B, which is acting along that direction, and let at the given instant of time when we are calculating the forces, we take the direction or the angle between the plane of the coil and the magnetic field to be theta. So the current I moves from M to N. This is the current I that is moving from M to N, and it is making an arbitrary angle theta. So F2, the force that acts, is equal to I, and the distance obviously is B. So I B cross B, B small b, that is the direction, that is the length vector in that case, is directed along the flow of current from M to N. And if we take the vector laws, cross product laws, then we have IBB sine theta, and the direction is going to be in the downward direction. If you use it properly, you have F2 to be acting in the downward direction. You can zoom in if you're having trouble with the figure. You can zoom in. So it's acting in the downward direction. Let me just represent that by that arrow marked in the downward direction. Now in that segment along NO, F3 is going to be I, again the distance now is L cross B, and this is ILB, and the angle is obviously 90 degrees, and from the vector laws that we have, the law of cross product, the right hand thumb rule, we can use it, and what we find is IL cross B is going to be out of the plane. So this is a dot encircled, which is the usual representation for out of the plane. So we have the force over here to be dot encircled. So this is F3. It's acting along the entire line. I have just marked it there so that I do not overlap with any notation for I and the arrow over there. And finally, along OP, we have F4, and any guesses where we are going to end up with the direction over here? Well, you might have guessed it right. The angle is obviously sine 180 minus theta, because the current is now in the direction from O to P, and the magnetic field's direction does not change. So it is sine 180 minus theta, which is obviously going to be sine theta. So IBB sine theta, but now it's directed in the upward direction. This is F4. So we have the forces F1, F2, F3 and F4 that are acting on the four arms, you can say, or segments of the rectangular coil. The coil, if it is allowed to rotate about an axis passing right through that longitudinally, that is the axis can be taken. Let me use another ink for that, a lighter one, I suppose. So this is the axis about which it will be free to rotate. So the axis of rotation has been provided along that line. So the forces F2 and F4, as you can see, they are cancelling out each other. F2 and F4, the forces being equal and opposite, will be cancelling out each other. The forces F1 and F3, you might say, are equal as well, but they won't be along the same line, as we'll be seeing in the figure below. This figure that we have over here from M to N. Now on that segment through PM, which is acting on that line which is ending at M, we have the force to be acting in that direction. This is F1. And then we have the point N from which the other segment starts downward, and we have that force to be acting out of the plane, and this is F3. Now those two forces, had they been along the same line, they would have cancelled out each other, but they are not. They are not along the same line. I'm redrawing that for you. This is that line, segment B, and the forces that we have at the point M and the point N are F3 and F1, and irrespective, it will be irrespective of the direction of flow of current. Even if the flow of current was counterclockwise, the forces would have interchanged with the direction, but the case would have been the same. Now the magnetic field, if you remember, was flowing in this direction, where it was making an angle theta with respect to the coil, plane of the coil, that is. So this is exactly the angle between those two forces, not the angle, but the the angle that the plane makes with the magnetic field is continuing in this direction. Now, if we consider the component the uh, of that segment, we have b cos theta. And if you observe closely, that b cos theta is the perpendicular distance between the two forces, separating the two forces. Now, the two forces, they obviously constitute a couple, and this coupling force leads to a torque that is developed and causes the twist along that rectangular coil. So what we end up with is that we have the value or the magnitude of the torque that acts due to these coupling forces. The torque is given by the relation of if they are equal forces, obviously coupling forces. So either of the coupling force multiplied with the perpendicular distance separating the two forces, perpendicular distance separating the two forces, that is the coupling forces. And here we therefore have tau, which is represented by tau, to be equal to either force, that is ILB, the magnitude of the force, multiplied to the perpendicular distance, which is b cos theta. And now we have I L times of b cos theta, and if you know what L times of b there, it will be the area of the coil, which is the length multiplied with the breadth. So we have IAB cos theta. This is the value of torque. Now this value of torque, this is in terms of the magnitude. Now this is for a single coil. Imagine we have multiple coils wound in that particular plane. Then we would have had the same magnetic field for each coil, and therefore, just like the cases that we have studied earlier, the value of the torque will increase n times. For n number of coils, the torque now becomes n times of IAB cos theta. Now this is the case of the magnitude. Now if we obviously have two vector quantities over there, area, remember, is a vector quantity, as well as the magnetic field. Now the angle here between the area vector and the magnetic field, if I were to redraw that top view, which is one of my favorite views in this topic, this top view enables us to obtain the angle between those vectors. Now this is the B vector, and this is the line, the direction of current, that is. So the B vector, and it was making an angle theta with respect to the segment which was carrying current along that line, and this is the area of the coil. This is the area vector of the coil, and let that area vector be directed, let me draw it clear. So that is the area vector which makes an angle, let us say alpha, and from that figure, as you can clearly see, we have alpha plus theta to be equal to 90 degrees. So for cos theta, we have it to be equal to cosine of 90 minus alpha, because theta is simply 90 minus alpha, and that is equal to sine alpha. So that means this value of torque that we have obtained is now in the form of sine, which is equal to NIAB sine alpha. And whenever there is a sine alpha involved, it's not clear there, so I'm writing it over here onto the left hand side, that vacant space. Torque is equal to NIAB sine alpha. And whenever there's a sine alpha, you can twist your head to read that. Whenever there's a sine alpha involved, we can have the vector terms pretty clearly explicitly written as tau, which is a vector quantity of course, is equal to Ni A cross B. Remember, it's A cross B, not B cross A. Considering the vector notation, because it is not associative, as you know, the case of cross products. A cross B is not equal to B cross A, so that means the area vector needs to be mentioned first, followed by the magnetic field. Now this relation, or even this relation, both those relations are very important in defining the principle of working of the moving coil galvanometer, which is to be discussed in the next video in this series. So till then, thank you for watching.